So today we're going to continue our discussion of networking. We're going to, if you remember from the last two times, we've talked about these two different layers of the network stack so far. We talked about the link layer, and we talked about the network layer. And today we're going to talk about the end-to-end layer. And what we've talked about so far has been a network stack that provides this abstraction of being able to send a message from one machine to another machine across a number of links on a network. And this network stack that we've talked about is, if you'll remember, a best effort network. So a best effort network, as you'll remember, is a network that is subject to losses. So some messages may not be properly transmitted from one point to the other point. It's subject to the possibility of reordering of messages, as messages may take, say, for example, different routes through the network. And it's subject to delays and congestion, typically due to queuing within the network. So today what we're going to talk about is the end-to-end layer. And the end-to-end layer is going to be the way that we're going to get at finally addressing some of these best effort network properties we've been kind of skirting around for the last few lectures. In particular, today we're going to focus on the issue of loss. How do we avoid losses within the network? And we'll talk a little bit about this problem of reordering. We're going to save the discussion of delays and congestion for next time. So the end-to-end layer, in addition to helping us deal with these limitations of a best effort network, provides a few other features that we need to mention. So the first thing that the end-to-end layer does is it provides the ability to multiplex multiple applications on top of the network. So the network that we've talked about so far is one in which there are these two endpoints, two computers that are connected to each other, and they're transmitting a sequence of messages. But we haven't really said anything about how those messages get dispatched to different applications that are running above the network layer. The other thing the end-to-end layer provides for us is the ability to is fragmentation of messages. Okay, and fragmentation is really about the fact that the link itself may have some maximum size message that it can physically transmit, because that's say for example, the maximum size message is how long the sender and receiver can remain synchronized with each other. So what the end-to-end layer often does is it provides the ability to take a longer message and fragment it up into smaller chunks or fragments that it transmits each of those fragments independently as a separate message across the network. So just to sort of illustrate how these things are dealt with within the end-to-end layer, let's look at a little illustration. So suppose we have some set of applications that are connected up to the end-to-end layer. Okay, so these applications, the idea is going to be that when a message arrives over the end-to-end layer, it's going to be dispatched to one of these applications by looking at a special number that's in the header of this message that comes in. So this number is often referred to as a port number, and each application is going to be running on one of these ports. So oftentimes these ports are sort of running at well-known addresses. So we talked about this numbers very briefly earlier. For example, web servers run at port number 80 in the TCP protocol. So if you want to contact a web server at a particular machine, you talk to port 80. Other times, applications will send the port number that they're listening at in the message that they're in a message, or two people will exchange the port numbers through some out-of-band protocol, say by telling your friend in an email that he should connect your server because it's running on port X. So this is the way that messages now are going to arrive into the end-to-end layer from the network layer, and these messages are going to have in their header information about which port they should be dispatched to. So the other functionality of the end-to-end layer, I said, is fragmentation. And fragmentation is about taking a message that's being sent down from one of these applications into the end-to-end layer. And then that message on its way to the network layer gets fragmented up into a number of chunks. So these are each of these little chunks in this message is called a fragment. So these are sort of two, so oftentimes we talk about it, one common end-to-end layer is one that provides an abstraction that's called a stream. So a stream is simply a flow of messages or data from one endpoint to the other, one application to the other, and where the segments in that stream are guaranteed to be delivered, are loss-free, so there are no missing segments or missing messages, and they're in order. So the application knows that the data that it receives is going to be in the order that the receiver knows the the data it receives is going to be in the order that the sender sent it out on the channel, and there won't be any missing messages. So this sounds like a pretty convenient abstraction, and it's one that is often used in applications, and in fact, the stream abstraction is the abstraction that the TCP protocol provides. Okay? So just to sort of make it clear, I just want to look quickly at a simplified end-to-end header format. So we looked at the header formats for the other layers last time, and this is just showing some of the things that you might expect to see in an end-to-end header. There, of course, there are additional things if you go look at the TCP header, but these are the ones that mostly matter from the point of view of this class. So there's a source port which allows which specifies which port the sender of the message is listening at on the other side. There's a destination port which specifies which port number this message should be sent to on the receiver side. There's something called the nonce. The nonce is just a unique identifier. It's just a thing that uniquely identifies this message as far as the conversation between the two endpoints is concerned. For the purposes, a common kind of a nonce to use is just a sequence number that gets incremented by 1 every time an additional message is sent. And then oftentimes in the end-to-end layer, there's also some checksum information, something that allows you to verify the integrity of the messages that are transmitted out over the network. And we do this at the end-to-end layer. We saw that the checksum sometimes appeared in the link layer before. They also appear at the end-to-end layer because it's important. It's possible that, as you guys read in the paper about end-to-end arguments, the end-to-end argument, oftentimes we want to verify that a message is correct at the end-to-end layer or at the application layer, even if we have already maybe verified that that was the case at the link layer, because the message could have been corrupted somewhere above just the link layer, right? So this is sort of the abstraction that the end-to-end layer provides. Notice that the header format here doesn't actually include, it doesn't include, for example, the addresses of the endpoints, the IP addresses. That's because the IP addresses are in the IP header. So remember, this is just the additional information that's added by the end-to-end layer and is used to dispatch from the end-to-end layer to the applications that are running above it. Once we're dealing with the end-to-end header, all of the packets have already been transmitted across the network, and in fact, we don't need to know what the IP address is anymore because this is happening on the local machine, and all the applications are running at the same IP address. Okay, so but the other things that we said so I said today we're going to focus mostly on the ability of the end-to-end layer to mitigate these problems of losses. So this is sort of the abstraction that the end-to-end layer provides, but what we want to look at now is how does the end-to-end layer actually deal with loss? And we're going to talk about two different techniques, or there's two different components to dealing with loss. So the first thing we want to do is we want to make sure that no packets get lost during transmission, and the way we're going to do that is providing what we call at least once delivery. The reason I put at least once in quotes here is that I'm going to talk you through a protocol, and this protocol is going to guarantee that a message gets received by the receiver as long as, for example, the receiver doesn't completely fail or the network doesn't completely explode. So it's always possible that messages can be lost because there can be some physical failure that makes it impossible for the messages to get through. But as long as it is possible for the message to get through, there's a very high probability the message will in fact get through. And if the message doesn't get through, what this at least once delivery protocol is going to guarantee is that the receiver knows that the sender may not have actually received the message. Okay? So then once we talk about at least once, we're going to talk about something we call at most once delivery. And the issue with at most once delivery is that the at least once protocol that I'm going to sketch out is going to generate duplicates, and we're going to need to make sure that we can get rid of some of the duplicates. And these two things together are going to provide what's known as exactly once delivery of messages. Okay. So let's start off by talking about our at least once protocol. This protocol is going to guarantee that, if at all possible, the message will be received by the receiver. And the way that we're going to do this is really very straightforward. We're just going to have the receiver send a message back to the sender that says, "I got the message." So the receiver, when it gets the message, sends this what's called an acknowledgement back. Sometimes abbreviated ACK. Indicating that the message was received at the other end. Okay, this is just going to be sent back to the receiver directly. So in order to send this acknowledgement, though, we're going to need a way for the receiver to refer to the message that the sender sent. Right. So we want the receiver to be able to say, "I received this message that you sent to me." And one way that the simplest way to be able to do that is to just use this nonce information that's in the packet. So we said the nonce is a unique identifier as far as the two endpoints of the conversation are concerned. So the acknowledgement is basically just going to be the nonce of the message. Okay. So let's look at how this works in a simple example. So the idea is that the sender, at some point, is going to send a message to the receiver, and this message is going to contain information like, it's going to have the address of the sender, the address of the receiver, the ports on both ends the message is supposed to be sent to, this nonce information that uniquely identifies the message, and then whatever the data that needs to go in the message. Now, when it sends this message, what's going to happen is that the sender is going to keep this table of pending messages. So the sender is going to keep a list of all the messages that it hasn't yet heard acknowledged. And then at some point, and it's going to keep, for example, if this say that the name of this message is 1 and the nonce for this message is X, is going to add that information into its table. Now, at some point later, the receiver is going to send an acknowledgement for this message 1 back, and it's just going to have the sender and the receiver IP address, the port number of the receiver, and the nonce, which the sender is going to use in order to remove this entry from its table. So once the sender receives an acknowledgement for a message, it no longer needs to keep any state about it because it knows that the receiver has received it. Okay, so how does this do us any good? How is this at least once? Well, let's see what happens when there's loss that occurs within the network. So the idea is very simple. Suppose that the sender sends out a message 2 this time, and that message somehow gets lost in transit through the network. So the network drops the message either because of congestion or because some link failed and it doesn't get through. The idea is that the sender is going to keep a timer associated with every message that it sends. And this timer is going to be a timeout value that's going to tell the sender when it should retry transmitting this message. And the sender is just going to retry transmitting messages over and over and over again until the message actually gets through. So in this case, it sets this timer for time tr1 at the same instant that it sends out this message. And then when time tr1 arrives and the message hasn't yet been acknowledged, the sender is, so after this retry interval time, the sender is just going to try and retransmit the message. So now in this case, the receiver has successfully received the message. But notice that the sender doesn't actually know that the receiver has received it. We can see it from the diagram, but there's been no feedback that has come from the receiver yet. And now suppose that the receiver sends its acknowledgement for this message, and along the way, the acknowledgement gets lost, right? So this could happen just as easily as the original message being sent out. So now, in this case, our retry mechanism continues to work. And after this retry interval and time tr2 is reached, the message gets resent. And then, in this case, finally, the message is actually received. And we can go ahead and remove it from the pending message list. So this process, the sender is just going to continually retry transmitting these messages until it gets an acknowledgement from the receiver. It's actually, in practice, it's the case that the receiver will only retry a fixed number of times because, as we said, there are certain situations in which the network can just be simply unavailable. Suppose there's no network connection available to the transmitter, to the sender. Of course, at some point, it's going to make sense for it to give up and stop trying, and then it will report an error to the user. The other thing to notice about this protocol that we've described here is that the receiver has received 2 copies of this message. So that seems a little bit problematic, right? If this is a message that says withdraw $10,000 from your bank account, we don't probably want to process that message twice, right? That might be problematic. So we're going to address that issue when we get to talking about at most once delivery. But just bear in mind for now that these duplicates can occur. There's another subtlety with this protocol that I've described here, though. Does anybody see something that's a little bit suspicious about this diagram that I've shown here, or a little bit weird about the way I've shown it? Yeah? Okay, right, good. So there's this question about how are you going to set the retry interval for these messages, right? So what I've shown here is that the retry interval is short, and the first time we sent and received this message, in fact, the time that it took us to do that appeared to be quite long on this diagram. Right? And so, in fact, what would have happened if we had done this is that the sender would have retransmitted this message several times, even though the receiver had actually received the message and the acknowledgement was on the way back to us correctly. It's just that we didn't wait long enough for that acknowledgement to come back to us. So there's this question about, well, how are we going to pick this timer interval so that it's appropriate for the network that we're running on? And this turns out to be kind of an interesting and challenging problem. So there's this question about how long do we wait before a retry? So a simple answer for how long we should wait is, well, whatever the round trip time of the network is, however long it takes for a message to reach the receiver and then for the acknowledgement to be sent back to the sender. So we call that the round trip time, or the RTT. So we'd like to wait at least RTT, right? But the problem is that RTT is, this round trip time is not necessarily going to be constant over the whole lifetime of the network. So let me show you what I mean. This is a plot of some round trip time information from a wide area wireless link. So these transit times are very long here over this link. They're sort of order of thousands of milliseconds. So the average transmission time is 2.4 seconds here. The standard deviation, which is a measure of the variance between these different samples, is 1.5 seconds. So there's a lot of sort of bouncing around of this signal, and it's not as though the round trip time is just it's saying that expecting the round trip time to simply be a single constant value isn't a very good idea. So if we want to set the timeout just to RTT, that's going to cause us, if you think about this for a minute, if we set it just to be RTT, which is, say, for example, maybe the average, the average round trip time that we've measured in a signal like this, well, half the time we're going to be, some significant proportion of the time we're going to be above the RTT, right? Because, if just picking the average, there's going to be many samples that are above the RTT. So instead, we want to do RTT plus some slop value, something that's sort of some adjustment factor that gives us a little bit of extra sort of leeway in how long we wait. But of course, we don't want to wait too long, because if we wait too long, then we're not going to actually retransmit messages that were in fact lost. Okay, so let's look at how. So that's sort of a simple, intuitive argument for how we should do this. what I want to do now is just quickly take you through the way that these round trip times are done. These round trip times are estimated in the TCP protocol. And the way this is done is really pretty straightforward. The idea is that we want to estimate the average RTT. So one way that we could, and then we also want to estimate the sort of variance, which is going to be our slop number. Okay. And the way that we want, so one way we could compute the average RTT is to keep this sort of set of samples of all the round trip times. So I have maybe 20 points, I have whatever it is, 20 points here that are samples of the round trip time. So I could take this set of 20 numbers and compute the average of them, and I could recompute the average every time a new number comes in. The problem with that is that I have to keep this window of all the averages around. So instead, what we want to do is to have some way of sort of updating the average without having to keep all the previous values around. And there's a simple technique that's commonly used in computer systems called an exponentially weighted moving average, which is a way that we can keep track of this average with just a single number. So this is the EWMA. And what the EWMA does is it's given a set of samples, say S1 up to some most recent sample, S new. What the EWMA does is computes the incrementally adjusts the RTT according to the following formula. It says the new RTT is going to be equal to 1 minus alpha. So these samples are samples of round trip times. Okay, like this number here. So these are numbers that we've observed over time as messages have been transmitted back and forth. We're going to take some number 1 minus alpha times S new, our newly observed round trip time, and we're going to add to that some alpha times the old round trip time. Okay? So what this does is basically it adds into it computes the RTT as some weighted combination of the old round trip time and the newly observed round trip time. And if you think about this for a minute, if we make alpha, so alpha is, in this case is going to be some number between 0 and 1. And if you think about alpha being 0, if alpha is 0, then the the newly computed round trip time is just equal to S new, right? And if alpha is 1, then the newly computed round trip time is just equal to whatever the old round trip time was, right? So the new sample has no effect. So as we move vary alpha between these two extremes, we're going to weight the new round trip time more or less heavily. Okay, so this is not going to perfectly compute the average of the samples over time, but it's going to give us some estimate that sort of varies with time. The other thing we said we want to do is compute what the slop factor is. And this slop factor is just going to be, we just want this to be some measure of the variance of this signal. So in particular, what we want it to be is, just going to push this up so I can write. Slop is going to be equal to some factor beta times some variance of this, some number that's the variance. And what I mean by variance is simply the difference between the predicted and actual round trip times. So if our formula says that this round trip time given a sample, the round trip time should be 10 milliseconds, and the next sample comes in and it says the actual round trip time was 20 milliseconds, then the variance we would say that the sort of this deviation, the difference between those two things would be 10 milliseconds. Okay, so let's see how this works. I'll show you now the pseudocode for how this actually works in the internet, and it should be pretty clear what's going on. So what we're going to do is we're going to keep a set of variables one of which is called SRTT. So this is almost exactly what the TCP protocol does. So we're going to have SRTT, which is the current round trip time estimate. And then we're going to have this thing we're going to call RTT_dev, which is the deviation, the current estimate of the sort of variance of this round trip time. And we're going to initialize these two numbers to be something that seems reasonable. We might say the round trip time is 100 milliseconds and this RTT_dev is 50 milliseconds. And now what we're going to do is we're going to just, every time a new one of these samples of the round trip time comes in, we're going to call this calc RTT function. What the calc RTT function is going to do is it's going to update the old, update the round trip time using this formula that we've seen here. And in the case of TCP, people have sort of experimented with different values, and the number that is typically used is that you sort of 1/8. A number that is commonly used is that sort of use alpha. You set alpha to be 7/8. So that means that you sort of add in 1/8 of the new number and use 7/8 of the old number. So this is not going to, a new number that varies a lot isn't going to change the overall round trip time, estimate of the round trip time terribly dramatically. And we're going to compute the deviation as I've shown here. We're going to take the absolute value of it, and then we're going to keep some running estimate of the round trip time, again using one of these sort of exponentially weighted things. So in this case, we're going to weight with this setting the value of the weight here to 3/4. Okay, so that's a simple way to compute the round trip time. And now, given the computation of the round trip time, what we need to do is to compute the timeout value that we should use. So in what we said is the timeout value we want to use is RTT plus some slop. And in the case of TCP, a commonly used slop value might be 4 times the estimate of the deviation. So the idea is that we want the slop value to be larger if the round trip time varies more. If the round trip time is practically constant, we don't want it to vary much. We're sort of happy if we're we don't want if the round trip time is practically constant, then the timeout shouldn't be very much longer than that round trip time, because that's going to suggest that we're going to be waiting longer than we need to time out. If the round trip time varies very dramatically, we need to wait a relatively long time in order to be sure that the message, in fact, has been lost, as opposed to simply taking a long time for the acknowledgement to get back to us. Okay, so this is what we've seen so far now is we've seen how we can build up this at least once semantics using acknowledgements. And we've talked about how we can go ahead and set these timers in order to allow us to calculate the round trip time for a message. And these timers are going to allow us to sort of decide when we should retransmit a message. But we also saw how we have a little bit of a problem in the at least once protocol. And the problem is that we can generate duplicates. So in order to avoid duplicates, we need to introduce this notion of at most once. Okay, so the idea with the at most once is that we want to suppress duplicates. And duplicate suppression, it turns out, it works a lot like the way that acknowledgements work on the receiver side, or on the sender side. So on the receiver side, we're going to keep a table of all the nonces of all the messages that we've heard, and we're only going to process a message when we haven't already processed that message, and we're going to tell whether we've already processed it by looking in this table of nonces. So let's look at an example. So here we are this is sort of, I was showing you the protocol, a stage in the at least once protocol that we were in before. So we've already sent message 1, it's been successfully acknowledged, and you notice that we have this table of nonces, received messages, that is at the receiver, and in this table we have received this message with nonce X. Okay, so now when the sender decides to send message 2 with nonce Y, it sends it out, the message doesn't arrive, we time out, we retry, and this time the message is successfully received. So what we do is we go ahead and add the nonce for this message into the table on the receiver, and then the receiver goes ahead and sends the acknowledgement, but the acknowledgement is lost. So again, the sender times out, resends the message, and this time when the receiver receives this message, it's going to look it up in the received messages table, and it's going to see that this is a duplicate. It already has seen a message with nonce Y, so it's not going to process this. But it needs to still be sure that it sends the acknowledgement for the message. So it doesn't actually do anything. It doesn't actually process this message. It doesn't pass it up to the application so that the application can look at it, but it still sends the acknowledgement so that the receiver knows that the message has been received. Okay? So this is fine, but if you think about this for a second, this table of received messages is now just going to be kind of growing without bound, right? Because every time we receive a message, we're going to add a new message to this table of nonces, right? And this is a problem. I mean, if we're sending, thousands of messages out over the network, then this table is going to become very, very large. So what are we going to do about it? Well, we're going to do sort of, again, the obvious thing. We're going to have the sender send some additional information that lets the receiver know which messages the receiver has actually heard. So a common way that this might be done is to simply, along with each message that gets sent, piggyback a little bit of information, for example, that contains the list of messages that the sender knows that the receiver has actually received, right? So when a sender receives an acknowledgement for a message, it knows that it's never going to have to request that it's never going to resend that message anymore. And so there's no reason for the receiver to keep that message in its table of received messages, because it's never going to be asked to acknowledge that message again. So we can attach a little bit of information to the messages that we send that indicates sort of which messages we've completed up to this point. Okay? So this is a simple way in which we can sort of eliminate these messages that are hanging around. These messages that are sort of left in our table of received messages are sometimes referred to as tombstones, which is kind of a funny name. But the idea is that they're these messages that are kind of hanging. They're the sort of remnants of a dead message that's hanging around that we're never going to need to process again, but it might just be sitting in this table. And we're able to get rid of some of the tombstones by piggybacking this information onto the ends of the messages that we retransmit. But you have to realize that there's always going to be a few messages left over in this received messages table, because if we use this piggybacking technique, because we're piggybacking messages, piggybacking the list of done messages onto messages that are sent. So if the sender never sends any more messages, then the receiver is never going to be able to eliminate any of the tombstones from its list of received messages. Okay, so now what we've seen is a simple way to provide this sort of notion of at least once and at most once delivery. And so as I said before, taken together, this is sometimes called exactly once, an exactly once protocol. And this variant of this protocol that we've seen is called a lockstep protocol. Okay? So it's called lockstep because the sender and receiver are operating in lockstep. The receiver sends a message and then it waits for the sender sends a message and then it waits for the receiver to send an acknowledgement before it sends any additional messages. Right? So we're always sort of sitting here waiting for the sender is sort of basically spending a lot of time idle waiting to receive an acknowledgement. And if you think about what this means in terms of the throughput of the network, it's kind of a limitation. So let's do a simple calculation. So suppose that we said that packets, that the segments that are being sent in this network these things that are being sent back and forth and being acknowledged are, say, 512 bytes large. And suppose we said that it takes the round trip time in the network is, say, 100 milliseconds, which might be a common round-trip time in a traditional network. Well, the throughput of this network is going to be, the maximum throughput of this network is going to be limited by this number, 512 bytes divided by 100 milliseconds, right? The round-trip time is 100 milliseconds, and so we have to wait 100 milliseconds between each transmission of messages. And the sort of size of a message is, if the size of a message is 512 bytes, then we're going to be able to send 10 of these messages per second. So we're going to send sort of approximately 50 kilobits per second. Okay, that's not very fast, right? If we want to send, to modern networks are often capable of sending, tens or hundreds of megabits a second. So we would like to be able to make this number higher. So this is a bit of a performance problem. And the way we're going to do this is by making it so that the sender doesn't wait to receive its acknowledgments before it goes and sends the next message. So the sender is going to start sending the next message before it's even heard the first message being acknowledged. So we're going to have multiple overlapping transmissions. Okay? So let's see a really simple example of how this works. So the idea is now that the sender it's going to send a message, and then before it's even heard the acknowledgement from the receiver, it's going to go ahead and start sending the message. At the same time, the receiver can go ahead and acknowledge the messages that have already been sent. So you sort of see what's happening here is that as time passes, the additional messages are being sent, and the acknowledgement for those messages start being sent as soon as possible. So we have a whole bunch of messages that are kind of flying back and forth within this network. And these, I've only shown the sort of yellow, red, and blue messages actually being acknowledged here. The white messages aren't being acknowledged, but of course there would be acknowledgments flowing for those as well. So this seems really good, right? Now we can send messages basically as fast as we can cram them onto the network, and we sort of don't have to wait for the acknowledgments to come back anymore. So in effect, what we've said is now the throughput is simply constrained by how fast we can cram the bytes onto the network. But this is a little bit of an oversimplification, right? Because this is sort of ignoring what it is that the receiver, suppose the sender is just sending data as fast as it can. Well, the receiver has to receive that data, has to do something with it, it has to process it, it has to take some action on it. Right? And so it's very possible, or very likely, in fact, that if we cram data at the receiver in this way, that the receiver is going to become overloaded. Right? The receiver has some limited amount of data that it can buffer or that it can hold on to, and we're going to overflow those buffers, and we're going to create a problem. So what we want to do is to have some way to allow the receiver to kind of throttle the transmission of the sender, to ask the sender to back off a little bit and not send so aggressively. Okay, so we call this the technique that we're going to use is called flow control. And it's basically just a way in which the receiver can tell the sender what rate it would like to receive data at. Okay, so this is going to be sort of receiver-driven feedback. And we're going to look at two techniques, basically, for doing this. The first one is a technique called fixed windows, and the other technique is a technique called sliding windows. Okay, and what we mean by window here, this is simply, a window is simply the size of the data that the receiver can accept, the number of messages that the receiver can accept. So this is can accept at one time. So the idea is we're going to send a window's worth of data continuously, and then once the receiver says that it's done processing that window, we're going to be able to go ahead and send a next window to it. So this first scheme that we're going to look at is called the fixed window scheme. And the idea is really very straightforward. The sender and the receiver at the beginning of communication are going to negotiate. They're going to exchange some information about what the window size is. So the sender is going to request a connection be opened, and then the receiver is going to say, for example, okay, let's go ahead and start having this conversation, and by the way, my window size is 4 segments. So now the sender can send 4 segments all at once, and the receiver can go ahead and acknowledge them. So we can have 4 segments that are sort of in flight at any one time. And then after those messages have all been acknowledged, the receiver is going to have to sort of chew on those messages and process them for a little while. during which time basically the sender is simply waiting. It's simply sitting there waiting. But notice that we were at least able to, the sender was able to do a little bit of extra work. It was able to send all 4 of these messages simultaneously. And then when this receiver has finished processing these messages, it's going to go ahead and ask for some additional set of messages to be transmitted out over the network. So notice that there's a little assumption here, which is that acknowledgments are being sent before the sort of receiver has actually finished processing the messages. So that it's sort of what the protocol that I'm showing here is that the receiver receives a message and it immediately acknowledges it without, even though it hasn't actually, the application hasn't necessarily processed this message yet. And the reason we want to do this is that application process, remember, it's already hard enough for us to estimate this round trip time using this estimated, this EWMA approach. And so trying to sort of also estimate how long it would take the application to process the data would further complicate this process of setting timers. So we usually just send acknowledgments right away. Okay, so this is the fixed size window scheme. And it's nice because now basically we've set this thing up so that the sender can send more, can sort of send more messages without waiting for the acknowledgments. But the receiver has a way that it can kind of throttle how fast the sender sends. It knows that it only has buffers for 4 messages, so it says my window size is 4. But we would like to do a little bit better, right? In particular, we would like to avoid this sort of situation where the sender, so in this case, we sort of have long periods where the network is kind of sitting idle, where we're not using available bandwidth within the network because we're sort of waiting. The sender perhaps has data to send, but it hasn't received the message to send more, the receiver can accept more messages. And the receiver maybe has processed some of the messages that it's received, but it hasn't yet sent this message it hasn't yet asked the sender to go ahead and send any additional data. So the way that we're going to fix this is to use something called the sliding window technique. And the idea is that when the receiver, rather than the receiver waiting until it has processed a whole window's worth of data, when the receiver processes processes each message within its window, so if this window is 4 messages big, once it's processed the first message, it's going to go ahead and indicate that to the sender so that the sender can then go ahead and send additional messages. So rather than this window sort of moving, rather than sort of getting 4 new messages at a time, what we're going to do is we're going to send our first 4 messages, and then we're going to just send 1 additional message at a time. So that's why we call the window, we say the window is sliding, because we're going to sort of allow the sender to send an additional message whenever it is that the receiver has finished processing just 1 message. And the way we're going to do this again, we're going to initially negotiate a window size. And then when the sender starts sending, it's going to do the same thing. It's going to send all 4 of these messages. I've sort of halted this animation in the middle of it so that I can show you an intermediate step. But what would really be happening here is the sender would sort of send all the messages that were in the window, and then the receiver would begin processing them. So now the receiver begins processing this message, and suppose the first message. So suppose it finishes processing segment 1 before it receives the segment 2 from the sender. So now what it can do is in its acknowledgement for segment 2, it can piggyback, again using this idea, it can stick a little bit of information onto the acknowledgement that says, oh, and by the way, I have finished processing one of these messages. You can go ahead and send 1 more additional message. You can slide the window by 1. Okay? So I'm going to hit the next step of this animation, and it's going to zip by really fast. I'll explain what's happening, but don't try and worry too much about exactly following the details. Okay, so what happened here is now what happens is that the receiver sort of continues to process these messages as it arrives, and then it continues to piggyback this information about the fact that it has finished sending some messages onto the acknowledgements, finished processing some messages onto the acknowledgements. If the receiver doesn't have any acknowledgements to send, which was the case for these last 2 messages that it sent out here that I have labeled send more, it may need to send these sort of slide the window messages out by itself without acknowledgements. So here it sends a couple of additional messages that say, go ahead and send me some more data. Okay, so in this way now what we've done is we've managed to make it so that the sender so that the sender can send additional information before all of the sort of messages in the initial window were processed by the receiver. So you see that before the sender sends, before the receiver actually requests, sends a message requesting a whole new window worth of data. So you see now that some of the sort of go ahead and send more messages from the receiver arrive at the sender after the time that the sender starts sending messages, this fifth and sixth message to be go ahead and processed. So we managed to sort of increase the amount of concurrent processing that we can do in this network. But there still are periods where the network is sort of idle, where we're not actually, where the sender and receiver are sort of not transmitting data. So we haven't done quite as good a job as maybe we would like. And the reason we haven't done quite as good a job as maybe we would like is that the sender, that when the receiver, so the property that we would like to enforce is that when the receiver says, go ahead and send me a new message, when the receiver says slide the window by 1, by the time that the next message to process arrives from the sender, we would like the receiver to not have reached the point where it's idle, where it has to wait. So we'd like the receiver's buffer to be big enough such that by the time its request for more data reaches the receiver, and by the time the sender, and by the time the sender's response comes back, we would like the receiver to still have some data to process. Whereas what's happened here is that the receiver finished processing all 4 messages in its buffer before this next message came back with additional data for the receiver to process from the sender. Right? So basically the problem was that the receiver's buffer wasn't quite large enough for it to be able to continuously process data while it didn't have quite enough data for it to be able to continuously process while it waited for the sort of additional data to arrive from the sender. So what this suggests that we want is to set this buffer size, to set the size of the window to be the appropriate size in order for the receiver to be able to sort of continuously process information if at all possible. So there's this question about how do we pick the window size. So let's assume, so the problem we have is that small windows imply underutilization of the network. Okay, because we have both the sender and receiver sort of sitting, waiting. There's times when there's no data that's actually that's being transferred across the network. So the question is then, how big should we make the window? And what we said is we want the window size to be greater than the amount of time we want it to be long enough so that the receiver, which say, for example, if the receiver can process some number of messages, rate messages per second, okay? The receiver can process this many messages. We want its buffer to be large enough that if it processes that many messages per second, that the amount of time for an additional messages for it to process, that it will still have messages to process by the time additional messages arrive from the sender. So the amount of time that it takes for a message to arrive, additional messages to arrive from the sender, from the time that this guy first sends this OK to send more message, right, is 1 round trip time of the network. So it takes 1 round trip time of the network for the sender, for the receiver to receive additional messages to process from the sender, and the number of messages that it will process during that round trip time is whatever its message processing rate is times the round trip time of the network. And so therefore, this is sort of ideally how we would set the window size in this network. Of course, we talked about before how it's tricky to estimate. This sort of EWMA thing that we do to estimate the window size is not a perfect estimator. But we're going to try and sort of set this. This is going to be a sort of good choice for a window size to use. And so typically the receiver is going to try and sort of use some rough estimate of what it thinks the round trip time is and the rate at which it can process messages when it informs the sender of the sort of the window size at the initiation of the connection. Okay, so this basically is going to wrap up our discussion of the end-to-end layer, or of this the sort of the loss recovery issues in the end-to-end layer. What we're going to talk about next time is this issue of how we deal with congestion, right? So we said that in one of these networks there can be all these delays due to queuing, and that these delays can introduce additional loss, and we call these delays congestion. And so what we're going to talk about next time is how we actually deal with congestion and how we respond to congestion. Okay, so we'll see you on Wednesday.